A sequence of real numbers, being a real function defined on a domain which is a subset of the set of real numbers, can be graphed just as any other real-valued function defined on a subset of the set of real numbers. It is often the case that such graph naturally extends to a graph of a continuous function defined on an interval of real numbers. If this is an infinite sequence, then this nicely links the concept of a limit of a sequence to the concept of a limit of a function at infinity. For example, the limit of 1 over n, or in other words of the sequence 1, 1 over 2, 1 over 3, and so on, is the same as the limit of the function f of x equals 1 over x, as x tends to positive infinity. Notice that the sequence in question, as a function, is simply a restriction of the function 1 over x to positive integers. In general, we have the following theorem. If a function f defined for all real numbers bigger than a certain number has a limit L at infinity, then the sequence an equals f of n, where n starts from any value big enough to be included in the domain of f, will have the same limit L. This can be summarized in a somewhat tautological formula. Limit of f of n as n approaches infinity is equal to the limit of f of x as x approaches infinity. The theorem above is useful in the sense that knowing how to compute limits of certain functions allows us to compute limits of the corresponding sequences, and vice versa. For example, the limit of the sequence n over e to the power n can be computed as the limit of the function f of x equal x over e to the power x, which, by L'Hopital's rule, is equal to the limit of the function g of x equals 1 over e to the power x, which of course is equal to 0. Analogues of limit laws for functions hold in the case of sequences. For example, the so-called squeeze theorem holds for limits of sequences. Given three sequences with relations an being less or equal to bn being less or equal to cn that hold for all n greater than a certain number, if the limits of the sequences a and c exist and are equal, then the limit of the sequence b also exists and is equal to the same limit. This can be applied in many interesting situations. For instance, to compute the limit of the sequence n factorial over n to the power n. The limits of outer sequences are both 0, so the limit of the sequence n factorial over n to the power n is also 0 by the squeeze theorem. Look up yourself further limit laws for sequences and explore how they can be applied to compute various limits. The concept of a limit of a sequence has numerous applications. Every irrational number is the limit of finite portions of its presentation as an infinite decimal. For example, the number pi, which is equal to 3.14159 and so on, is the limit of the sequence 3, 3.1, 3.14, 3.141, 3.1415, 3.14159, and so on. definite integral of a function is defined as the limit of a sequence of its Riemann sums. Limits of sequences also allow to conveniently express irrational numbers. For example, the irrational number e turns out to be the following limit. Namely, e is the limit of the sequence whose terms are 1 plus 1 over n to the power n.